This is a short presentation on my variation of a popular circuit, a digital piano based on a 555 timer. It uses relatively simple off-the-shelf parts to create a range of pre-selected frequencies which can be played back through a speaker. So first off, what is a sound wave? A sound wave is just a type of mechanical wave that propagates through a medium such as air as a result of the vibration of particles in the medium. The frequency of a sound wave, which we measure in hertz, is the number of compressions, where air molecules are pushed together, and rarefactions, where air molecules are spread apart, that pass a point, like one of our ears, per second. Higher frequency sound waves have a higher pitch, while lower frequency waves have a lower pitch. A loudspeaker has a diaphragm, usually a cone or a dome, attached to a voice coil, which is placed within a magnetic field. When we send an electrical signal through the voice coil, it creates a varying magnetic field which interacts with the permanent magnetic field of the speaker. This interaction causes the voice coil to move the diaphragm back and forth, creating pressure variations in the air, or sound waves. So to generate tones, we use an oscillator. An oscillator is an electronic circuit that generates a repeating signal like a sine wave or a square wave. Oscillators are fundamental components in a wide range of electronic devices where they're used to provide a stable and consistent signal. The frequency of the sound wave produced in this fashion matches the frequency of the oscillating electrical signal. So a 440 Hz signal will produce sound waves that cycle 440 times each second, which we perceive as the musical note A above middle C. This is my final circuit. It might look a little confusing at first, but it's much easier to understand with some analytical tools. Internally, the 555 timer consists of two voltage comparators, a flip-flop, a discharge transistor, and a resistor divider network. I recreated part of my circuit using Fallstad's Circuit Simulator. It's a really helpful tool for visualizing the way electricity moves around in a circuit. There are lots of common pre-built circuits to check out, but this one I plugged in myself based on my actual circuit. With this setup here, we're watching the capacitor as it charges through the resistors R1 and R2. When it reaches 2/3 of VCC, it triggers the upper comparator and changes the state of the flip-flop in the 555 timer, which turns off the discharge transistor and causes the output to go high. At this point, the capacitor starts discharging, only through R2. When the voltage across the capacitor drops to 1/3 of the supply voltage, the lower comparator triggers. This resets the flip-flop, turning on the discharge transistor, and the output goes low. The capacitor begins charging again, and the cycle repeats. You might have noticed this circuit slowed down a lot. We're looking at things in the millisecond range right now, so this is about 1/1000th speed. As I start to turn up the simulation speed, we can start to see how fast things are actually moving to produce the frequencies that we're trying to hear. By carefully selecting components in a GUI I developed using MATLAB, I can adjust the frequencies I produce. Here's what everything sounds like on a breadboard.